Hi, my name is Haekyu Park. I'm a computer science PhD student at Georgia Tech. Today, I'm really excited to share our experience in helping students learn how to do accelerated data science using GPUs through NVIDIA's RAPIDS library. Co-presenting with me is Polo, my PhD advisor. I worked with him as a teaching assistant of a large data science class with hundreds of graduate and undergraduate students, where I designed and developed a homework assignment that introduces students to NVIDIA Rapids. I'd like to first start with a quick overview of our research group at Georgia Tech, which helps provide some context for why we are interested in teaching GPU accelerated data science. Our research group, Polo Club of Data Science, consists of almost 20 PhD, master's, graduate, and postdoc researchers. We've been working on human-centered artificial intelligence, which intersects scalable machine learning, data mining, and interactive visualization and human-computer interaction. Our goal is to develop scalable, interactive, and interpretable tools that amplify humans' ability to understand and interact with billion-scale data and machine learning models. Polo has been teaching a graduate-level class called Data and Visual Analytics that introduce students to broad classes of techniques and tools for analyzing and visualizing data at scale. It emphasizes on how to complement computation and visualization to perform effective analysis. Today, we are excited to share our experience helping students in this class learn about using the NVIDIA RAPIDS library to scale up the data analysis. The course is an introductory data science class. Since it was first taught in 2013, the course has been offered almost every semester. The courses cover the state-of-the-art knowledge and practical skills in data and visual analytics to train students to become data scientists, to learn a breadth of analytic skills needed to gain insights into large data sets. It first gives students a bird's eye view of the data analytic building blocks, from data collection, cleaning, storage, to analysis, visualization, and presentation. Then dives into analytic principles and visualization techniques, such as web-based visualization based on D3, and scalable computation like Spark and Hadoop on cloud platforms such as Azure and AWS. Today, we focus on the analysis module, where students learn about machine learning and data science techniques. This module is also the best place for us to introduce students to GPU-accelerated computation techniques. When teaching GPU-accelerated techniques, we encountered three challenges. First, many students are new to GPUs. While they have some programming experience, many of them have not programmed for GPUs before. Second, we have many students in the class, which means whichever instruction approaches we decided to use, they needed to be able to scale to work for many students. Third, working with GPUs may mean that students need to either log on to a GPU-equipped server or to use the cloud, which naturally involves some extra steps and environment configuration that are new to most students. To address the first challenge of students being new to GPUs, we help them learn by building on experiences that are already familiar to them. Specifically, we observed that many students were already very familiar with popular Python libraries such as NetworkX, Scikit-learn, and Pandas. Therefore, when designing programming assignments to help students learn about how to accelerate data science through GPUs, we chose to use NVIDIA's RAPIDS framework, which provides APIs that are really similar to those of NetworkX, Scikit-learn, and Pandas. For example, Rapid's read CSV function for reading in data from a file can be used as the same way as it is in Panda's read CSV function. With these similar APIs, we provide students with a very gentle learning curve when moving from writing conventional CPU-based programs to GPU-accelerated programs. With these similar APIs, we provide students with a very gentle learning curve when moving from writing conventional CPU-based programs to GPU-accelerated programs. With these similar APIs, we provide students with a very gentle learning curve. We provide students with a very gentle learning curve. With these similar APIs, we provide students with a very gentle learning curve. We provide students with a gentle learning curve. With these similar APIs, we provide students with a very gentle learning curve. With these similar APIs, we provide students with a very gentle learning. We provide students with a very gentle learning curve when moving from writing conventional CPU-based programs to GPU-accelerated programs. With these similar APIs, we provide students with a very gentle learning curve when moving from writing conventional CPU programs to GPU-accelerated programs. Also, based on the similar APIs, students can easily compare the performance of CPU and GPU frameworks. Shown here is one of the visualization that student would create in the assignment. Horizontal axis here is the size of data, and the vertical axis here is the runtime of the k-means clustering algorithm. The red line is the runtime for the CPU-based algorithm from scikit-learn, and the blue line is the runtime for the GPU-accelerated algorithm provided by NVIDIA Rapids. The GPU-accelerated approach is orders of magnitude faster. The GPU-accelerated approach is orders of magnitude faster. To address our second challenge to support many students, we used hybrid platforms to scale up all of the students. Initially, we aimed to support up to about 250 students, which was the class size of the Atlanta campus version of the course. Luckily, we have an NVIDIA DGX-1 server, which is equipped with 8 Tesla V100 GPUs. However, even with such powerful hardware, 250 students was still far too many to support. Therefore, we decided that in addition to using DGX-1, we also support an alternative ways for students to complete the assignment by using Google's Colab Cloud GPU platform. We developed a Jupyter notebook for the assignment that could run on both DGX-1 and Google Colab. This way, students can choose whichever platforms they prefer. Here's a screenshot of the notebook showing how students may check the state of the GPU environment. We have made the notebook freely available to everyone. This link to download this is shown on the screen. For students who used DGX-1, due to an already deployed Docker image containing everything they needed, they could skip some of the steps that otherwise would be needed on Google Colab. After setting up the environment, students need to download the datasets for their machine learning algorithms. To help students get started with running the machine learning algorithms, you provide them with starter code for them to build on. Here, in part 1 of the assignment, the students start experimenting with CPU-based algorithms. Then in part 2, they move on to experiment with GPU-accelerated algorithms through NVIDIA RAPIDS. Our third challenge to address was about how to reduce the number of steps that students might need to go through when learning to work with GPUs, which often means that students would need to either log on to a GPU ecoserver or some cloud like Google Colab, which naturally involves some extra steps and environment configurations that are new to most students. We solved this problem by developing a carefully designed step-by-step guide describing both the high-level stats and low-level tasks that students might need to perform, such as how to log into a server, connect their local computer to the server with SSH tunneling, and how to set up the Docker image, and so on. Our step-by-step guide helps take a lot of this frustration out of the student's mind. We integrate the guide into the homework assignment. To sum up, we shared our experience in identifying and addressing the challenges when designing an instruction module that helps students learn about GPU accelerated techniques. To help students get started more easily, we provide a gentle learning curve and encourage them to build on APIs that they are already familiar with. To handle the large number of students, we use the hybrid platforms of a local DGX-1 and Google Colab on the cloud. To help students overcome technical setup steps, we provide a step-by-step guide. Besides solving the challenges, we are currently working on a few other improvements. For example, we are working on developing a better understanding of how many students that each local GPU may support. Our findings will help us better optimize the usage of our computation resources. We are also exploring a more efficient way for students to use Google Colab. Currently, to run Rapids on Google Colab, a Tesla 4 GPU or better is needed. However, GPUs are currently randomly assigned, which means students often need to refresh the session multiple times to get a GPU that supports Rapids. Based on our experience, a student could be required to refresh the session for as many as 10 times. Let me wrap up and summarize our takeaways. Through our instruction module, what students have learned is that GPU accelerated frameworks are easier to learn than they have expected. And for us, the instructors, what we have learned is that it's critically important that we carefully consider how to scale our instructions to large classes. Thank you for listening. The Rapids assignment is freely available at the URL on your screen.